Okay, now we move on to beams. So for beams, of course, we know beams is being referred to as long, straight structure which is supported and loaded in such a way that the external forces and couples, including the sections acting on it, lie in a plane of symmetry of its cross-section with all the forces perpendicular to its centroidal axis. So in this chapter, the basic concept that we are going to consider for the analysis of the beam using matrix stiffness method is based on the matrix stiffness formulation. So for this one, for beam, we have to take note that, okay, for the beam, we have to identify the distinction between global and local coordinate systems. So to start with, so we have here the illustration for our actual beam. So our actual beam consists of 3 members. So both ends are fixed and there is a roller at a certain joint. However, from the material for our beam, they're not all throughout the same. So now let's start to define or to distinguish our global and local coordinate system. So to identify our global coordinate system, of course, we are trying to have the structure coordinate system. So for this beam, we're going to choose our point of intersection or the origin for our global coordinate system or the structure coordinate system. So we have here our point. So this will be our point wherein we have to have the intersection of the x and y coordinate for our global or structure coordinate system. So for this one, if this will be our point of origin, so we can have here this will be our x axis, x coordinate. So you have here denoted by x, and this will be our perpendicular to that will be our y. So we have now our y coordinate. Now we are going to identify our member coordinate system or the local coordinate system. Based on our previous discussion for the plane truss, we're able to identify our member coordinate system for our structure. So the local coordinate system is also known as member coordinate system because we're going to identify the coordinate system per member. So for this one, if we're going to have here per member, so we have here our member 1, you have member 2, and member 3. So for member 1, so this will be our x of 1, you have your y of 1. To denote, 1 to represents member 1. Then we have our member 2, so you have here its specific coordinate system in the local coordinate system. So you have x of 2 and y of 2. And then for our member 3, so you have here our x of 3 and y sub 3. So now we have now identified our global coordinate system and member coordinate system or the local coordinate system. Now we move, okay, if we're going to observe class, we have to take note that we have different material. So if this will be denoted as I, both here because of they have the same material, that will be I. So member 3 is it has a different material, so that can be denoted as 2I. Now we're going to identify our degrees of freedom. So when the beam is subjected to an external load, of course, there will be the member will deform as it is subjected to an external load. So this is the deformation of the beam, and you have here the deformed configuration and the undeformed configuration as it is illustrated. So this one is the degrees of freedom or the displacement that may occur on our beam due to the external load acting on it. Of course, we learned that for the degrees of freedom, a member, there will be two degrees of freedom. You have translation, it will be there is translation and rotation. So in our planechas, we have identified that it is only subjected to translation along x and y direction. However, for the beam, it is subjected to translation and rotation. So the displacement is translation and rotation. However, since axial deformation is neglected on the beam, so therefore the translation is only along y direction. And of course, there is rotation. So which means that there will be two degrees of freedom, which is translation and rotation. Translation only along y direction since axial deformation is being neglected for the beam. So the degrees of freedom or the displacement along x direction is 0. So we have here translation along y direction and we have rotation for our beam. So if we're going to identify here our degrees of freedom, so we have here our beam. So we have here identified our member 1, member 2, member 3. And of course, you have your joint 1, joint 2, joint 3, and joint 4. Now, if you're going to identify the degrees of freedom, so let's start at joint 1. At joint 1, we don't have a degrees of freedom. Then if there is no degrees of freedom, you move on to joint 2. For joint 2, we have here a degrees of freedom. For this is a roller, so the degrees of freedom is rotation. So here, of course, in our previous discussion, we have a symbol arrow to identify for our degrees of freedom and an arrow with a slash for our restraint coordinates. So same symbol that we're going to make use. So we have here an arrow, of course, for rotation. We have an arrow. So for member 2, we don't have translation for a ruler, but there is rotation. So we have now 1 degrees of freedom. So this will be the symbol, which is an arc, an arrow that is somehow in curvature. So that will be our 1 degrees of freedom in rotation. Then move on to joint 3. For joint 3, this is a free joint. So which means we don't have a support. So there will be a presence of 2 degrees of freedom, translation and rotation. So how to number? We have to number first translation, then followed by rotation. So translation along y direction, so that will be numbered as 2. Then you have rotation numbered as 3. So we have now identified our degrees of freedom. Then we move on to the joint 4. So joint 4, this is also fixed. So which means that we have no degrees of freedom at joint 4. So now we have identified our degrees of freedom. So there are 3 degrees of freedom if we're going to write that in matrix form. So that will be D to represent degrees of freedom. That is D sub 1, D sub 2, and D sub 3. So now we have identified our degrees of freedom. Now, if we're going to go back again to joint 1, we don't have degrees of freedom, which means that we have restraint coordinates. So going back to joint 1, so we end up at number 3. So we're going to continue. So we have restraint coordinates along y direction, and of course for translation. So which means we have restraint coordinates, translation along y direction, and of course we have restraint coordinates for rotation. So it will have an arrow with a slash. So since we end up at 3, so we're going to continue our number. So we have to number first our restraint coordinates on translation along y direction, so that is 4. Then followed by rotation number as 5. In joint 2, we have restraint coordinates for translation along y direction. So we have here an arrow with a slash and we denote that as 6. Then at joint 3, we don't have restraint coordinates. At joint 4, we have restraint coordinates. So we have 2. We have translation along y direction, and of course we have rotation. So we have to number first our translation along y direction. So we have here 7, and we have here rotation, restraint coordinates for rotation, so that is numbered as 8. So if we're going to identify now the number of restraint coordinates, so we're going to have here our r. Our restraint coordinates is denoted as we have here 1, 1, 2, 3, 4, 5. So which means that we have 5 restraint coordinates. So that is the number of restraint coordinates. Now to identify the joint load vectors. We know the joint load vectors is in the position and location of the degrees of freedom. So which means wherever is the degrees, which means that if there is degrees of freedom, there is joint load vectors. So now at joint 2, we have degrees of freedom, rotation, so we have here p sub 1. Then at joint 3, we have translation and rotation. So we have here translation, we have p sub 2, then we have rotation, which has p sub 3. So which means now we have 3 restraint coordinates. So that will be p is equal to p, there are 3 joint load vectors rather. So this will be numbered as p sub 1, p sub 2, p sub 3. So we have now our joint load vectors. Now, if we're going to identify our reaction vectors basically is denoted by our, reaction vectors is denoted by R. So if we're going to identify the reaction vectors, there will be 5 reaction vectors because as we have identified in our previous discussion, the number of reaction vectors is equivalent to the number of restraint coordinates. So that is R to denote the reaction vectors, and that will be equivalent to, in matrix form, if we're going to write that in matrix form, we start with R sub 4, then we have here R sub 5, then we have here R sub 6, then we have R sub 7, and of course we have R sub 8. So we have identified now our reaction vectors, R sub 4, R sub 5, R sub 6, R sub 7, and R sub 8. So those are the reaction vectors that we have identified. Now for our problem, we have here identify by numbers the degrees of freedom and restraint coordinates of the continuous beam with a cantilever overhang shown in our figure. Also form the beam's joint load vector. So for this one, we have to identify the degrees of freedom, the restraint coordinates, and we have to identify the joint load vector. So this is our actual beam. So we have an actual beam. We have a force rotation, we have a bending moment 50 kips feet, and we have a vertical force at point D, which is 20 kips. Now we're going to identify our degrees of freedom. So we have identified here, we have member 1, member 2, member 3. You have to take note that this is our joint 1, then we have our joint 2, then we have our joint 3 and joint 4. So as we identify our degrees of freedom, so we simply have a roller. So we have here rotation, and we have here at the free joint, we have translation and rotation. So if we're going to identify, you have 4 degrees of freedom, and you have identified for our 3 restraint coordinates. For now, we have to identify our joint load vectors. So we have to take note that joint load vectors for this whole beam, if we're going to identify our joint load vector, so we have here P is equal to P sub 1, P sub 2, P sub 3, and P sub 4. So which means that compare this one to our actual beam. So if there is an existing load on that joint, you have the value for our joint load vectors. So P sub 1 is at joint 2. We have we have here 50 kips, so this is in a counterclockwise direction, take at negative. Then at joint P sub 2 is at joint 3. We don't have a load, so this will be 0. At joint P sub 3 is at joint 4, so we have an external load which is downward, so negative 20. At point P4 is at joint 4. We don't have an external load. Don't have an external load for rotation. We don't have a bending force, bending moment force, so this will be 0. So we have now the value for our joint load vector is P.